Welcome to week 5 of this course. This week we're going to study the LCD, and it's going to be a useful device in our projects. And there are obviously various different kinds of LCDs that can be used with the Raspberry Pi. And the particular one you've got with your kit is a specific model that allows you to put 2 rows of 16 characters on the screen. And this is a common type for IoT projects that you probably, if you just Google around, and you'll see people talk about this a lot. Now, this device, because it actually needs to handle quite a bit of data compared to what we had to do before. It was a fairly simple signal, with a buzzer, with the LED, even with the RGB LED. Things get a little bit more complicated when it comes to LCD. Now, when it comes to the screen display, there's different technologies. Like your cell phone, you may very well have OLED or OLED type of technology. And the LCD has been used on iPhone for many models too. So now I'm not going to talk too much about what LCD is. We're just going to, want to look at how we want to use it, how to communicate with it. So first of all, let's talk about the serial interfaces. Now, what are serial interfaces? The Raspberry Pi has GPIO pins that you're already aware. And those pins allow us to, connect additional devices to the Pi. And that will extend the capability of the Pi and interact with the physical world. And then there are some devices we need to have sort of a communication. There's a sort of data communication with the device. When it comes to data communication, there needs to be some kind of interface, some kind of protocol to communicate. Could it be between the Pi and that device? Or if you connect the multiple devices, then the communication could also be happening among those devices too. And the Raspberry Pi supports a couple of such communication mechanisms, and they are actually all serial type of communication. What is serial type of communication? Let's take a look at the difference. So there are actually 2 types of communication. It could be serial or parallel. The difference is how do we communicate with the device? So if we're going to look at a parallel interface, you have a device that's the receiving side that receives data. You have a device that's the transmitting side. And when the data is sent from the transmitter to the receiver, in the case of a parallel interface, in this case, we actually have, 8 bits. We have 8 bits, or, the size of a byte, sending over to the other side. They would be sent in parallel with 8 wires. So there's 8 data wires, and the data gets sent, the signal gets sent simultaneously, okay? Now, the other type of communication is called a serial interface. The name serial means one after the other. So this is what exactly this picture shows. The transmitter needs to send a byte. We're still talking about, let's say, the same data, 011000011, right? This is binary number, whatever that means. We can send in this data. Now we are only sending this data on a single wire, single data wire. And then we're gonna send these 8 bits one by one, starting with the most significant bit, ending with the least significant bit. So this is the serial communication mechanism. And then you are thinking, well, intuitively it seems like the parallel interface should be faster, right? You send multiple things simultaneously versus, well, in reality, it is actually the opposite. Why? The serial links actually can be clocked much faster than parallel links. Now, how is data getting sent? Let's say, you send this one byte over, and then you have more data to send. So typically, and then there's actually different styles in that respect. So in the case of this, let's assume our communication is synchronous. Synchronous means there is a clock that's synchronizing the data sending transactions. So basically you have pulse, upon each pulse, you send some data over, or the data is read. So there's timing of the signal, like when do you send a signal, when is a signal sampled or read, and that's precisely timed. So it's on a clock. And this clock frequency determines the speed, actually. If you clock the receiving or transmitting signal at a higher speed or higher frequency, then you can send more data within the same amount of time, right? So the serial communication is actually faster than parallel because we can actually have much higher clock frequency. And the reason that we can do that is because the parallel communication has a clock synchronization issue. You need to synchronize the signal across all as many different wires you're sending simultaneously. You need to synchronize that. Otherwise, it could be an issue with the so-called clock skew issue. The clock skew issue means the data is sent on different wires at different time, like different pulses, and that causes a problem. Like when you sample the data, is this bit part of this byte or part of the previous byte or part of the next byte, right? So it has to have that kind of synchronization going on. So that's one of the reasons why parallelism is not a good in this case. It's not as good as a serial. And also because the serial communication, we just use a single wire here, versus the parallel communication, we have to use multiple cables. So the serial connection requires fewer interconnecting cables. That simplifies things. That brings another benefit. Because it has less wires, less cables, there's less interference from the nearby conductors. So that is the interference is an issue called a crosstalk. Your signal could be interfering from one cable to another that causes inaccurate or errors in the data transmission. So the crosstalk issue that could be more of a serious issue in the parallel links, but less of an issue in the serial links. So because of these properties, the serial communication can be much faster than the parallel communication. And the most popular, I can say the most popular because the many devices, when it needs data communication, they are most likely you're going to see they support this protocol called inter-integrated circuit, or I²C. Often it's shortened as I²C. Now, just judging by the name, this really means is allows us to communicate between two integrated circuits. And that also kind of means it's for short distance communication. You know, could it be on the same board within, you know, a couple of inches or maybe a couple of meters, you know. And this protocol, the I²C, was actually invented in the early 1980s by the company called Philips. And the Philips company, this part of the company that does the semiconductors, now is called NXP. And it is very widely used for attaching low-speed peripheral integrated circuits. Now, why low speed? Low speed, well, this is relatively speaking compared to, you know, like CPU and memory. And so this is a kind of a for many of the devices actually that you may be familiar with, like you know, even your camera, you have a cable connected to a, you know, computer. You know, okay. So first of all, USB and the universal serial bus port is everywhere, right? So that USB port uses a serial communication and potentially be using actually the I²C protocol as well. And the I²C protocol actually supports different speeds. And the I²C is not necessarily used for like really fast communication, by the way. It's relatively low speed. It kind of is up to like about, you know, 3 megabits per second. So when you guys are really high speed, you know, the USB obviously has its own protocol, USB 2, USB 3, you know, that has different standards how the data is getting transmitted. But the I²C, even in that case, is used for some smaller functions in that whole circuitry. And there's a subset of I²C called SM bus. SM bus is system management bus. The SM bus was created by Intel. This was meant to be more interoperable because I²C it's kind of a low level. It doesn't, you know, define too much. There's kind of an interoperability issue, and kind of a lot of vendors have their own thing. So the SM bus became sort of popular, and many products actually started supporting it. Now, of course, if a device supports SM bus, then it also supports the I²C, because I²C is a superset of SM bus. And typically, it's very easy transition. You know, if it supports SM bus, basically they also can communicate on I²C. And the LCD display that you have, it communicates on I²C interface. And when you are programming with it, you could actually communicate with it with the SM bus library. So the SM bus is a particular protocol, how you communicate, how do you send the messages over, how do you transmit data, how the signal, the start and end. So we're going to take a look at the signaling of the data transfer. Just for a basic idea, I'm not going to go into too much detail of the electronics. And what you're seeing here is actually this name. You actually see these names on the devices. Many of the devices will have these names, and then even in your GPIO pin naming, you'll see these names as well. And this SDA stands for serial data. So this is the serial data signal, this serial, and then the other signal is called a serial clock. As I said, because this is a synchronous communication, is a clock to synchronize, when do you send data, when do you read data, that kind of stuff. And so this data signal, and you have a clock signal, and then so the sequence of sending let's say here we're sending n bits of data, and B stands for bit. And in this sequence, in order to communicate, it starts with a start signal. This start, each square here, actually consider this as a pulse. Basically one cycle of the clock. So within this one pulse, first we'll start with a start signal. The start signal will basically lower or pull down the signal. What is signal? Right? It's electrical pulse. Electrical signal, you have only basically two states. You have high voltage or low voltage. And there's a range of high voltage and then a range of low voltage. So within that range of high voltage is considered, logical 1. Within that range of low voltage is considered logical 0. So it starts. So when the lines are idling, they're always on high voltage. So the clock and the data line, they're on high voltage starting out. So when we start sending, first we'll pull down the voltage of this data signal, and then the clock maintains high, and this signals a start. This signals start of a transaction, actually. And then on the next pulse, and in fact, actually there is going to be a little bit of delay. Before it goes to the next pulse, the clock starts pulling down. And then in the middle, when it's in the stable low state, then this is the time for the data line to get ready for sending a bit. And either it maintains that low to signal, the first bit we're going to send is 0, or you pull that voltage higher to be 1. And they say, well, we're trying to send, either we're sending this B1 and maybe it's 0 or 1. This is the data we need to send, is 1 bit. And then at this time, when we're getting ready, the clock is at a low voltage. And then on the next pulse, the clock is pulled up into a high voltage, and then the data line maintains that signal. So during this stable phase of that clock signal, we read the data, either 1 or 0. And then the clock goes down again into low voltage, and so that the data line gets ready for sending the next bit, which can be 0 or 1 again. So this same process goes on and on. And it will send all, n bits. Now, after we send n bits, and then there's one last pulse for the clock. The last pulse for the clock go down to low voltage to 0, and the data line also pulls down to 0. Okay, so they're both at 0, and then the clock, pulls up to 1, and also the data line pulls up to 1 as well, and that is the final stopping signal. So we start and then we stop. So this is a one sort of a one transaction of sending n bits of data. So this is kind of at a little bit lower level. This is how this works. Now, I2C is not the only interface, as I mentioned earlier. There's other interfaces supported by the Pi. The other one is actually faster than I2C. It's called SPI, Serial Peripheral Interface. The Pi can support about, well, it has support for 2 devices. But if you want more, it gets more complicated. But typically, you can connect 2 of them fairly easily. Look at this diagram right here. And these are the names of those pins, by the way. If you look closely, you have these names. And then what does these names mean? I'm not going to go into too much detail of SPI, but I'll just tell you what those actually abbreviations mean. You look at those things on your pin naming scheme. And this is basically serial clock, okay, SCLK. And this is a master output, slave input. This is MOSI, and then MISO is the master input, slave output. This is defined in basically direction, which way the data goes, communicates next to a device. And the CS is the chip selection. On the Raspberry Pi, the pin both say CE, CE0, CE1. That's the chip enable. And that's the same as the CS, okay? In the I2C, the way you connect I2C, typically a device only uses 2 data cables plus a ground, or optionally you have a power, additional power as well. But the data communication, you got two wires. You have serial data, SDA, and then you have serial clock, SCL. Okay. So if you look at the Raspberry Pi pin names, you'll see SDA1, SCL1 at the physical pin number 2 and 4. No, so actually 3 and 5. Okay. So if you actually look at your extension board, and you'll find those at the physical number 3 and 5. Those are the 2 pins that we need to connect. Actually, when we connect, I'll explain a bit more, and let me finish this one now. The other serial interface protocol called a UART, that is called Universal Asynchronous Receiver and Transmitter. This is the asynchronous communication. Asynchronous means here we don't have a clock signal. It's not synchronized. Because it's not synchronized, actually it is slower. It's the slowest among the 3. And we're not going to study, we're not going to have a device actually will communicate on these things, but yeah, you will, in your own IoT programming, you will probably encounter some of those things. But the I2C is the most common that you'll see. And there's a couple of terms that I already kind of explained a bunch of them, and I'll leave this in the slide for you to read them. And for right now, I'm gonna move on to showing you the device on the breadboard. Okay. Yeah, so this is now, let me know if this is not the kind that you got. And so this, unfortunately they gave me a screen without the I2C, the I2C backpack. This is called I2C backpack. See this piece of chip that's behind. And I think this is the one you got. I actually got one from the school that is without it. You can connect the display directly to the Pi with multiple ports. It has many pins, by the way, on the, if you look at this piece, this is now connected with with the I2C backpack, and the I2C backpack is connected to it so that you can communicate with the LCD via I2C protocol. and it exposes these 4 pins over here, and 2 data. So actually, those are named. If you read those, if you just take this out, you'll read those. There's names SDA, SCL that we have seen. I explained. They also have the ground and the VCC. Now, VCC is for the positive voltage. We're going to connect a VCC to 5 volts here, and the ground, it goes to the ground, and the other 2 SDA, SC, excuse me. So SDA and SCL, they are connected to the GPIO pin, physical pin, 3 and 5. As I explained, this at the top left corner, you see SDA1, SCL1. So connect those wires accordingly to these pins. Now, I also noticed that these pins are male, and to connect to the breadboard, you actually need a male to female jumper cables. I don't know if the school has provided you those jumper cables. Now, when I got my set of cables, I did not get them. I asked them to order more. So we need the male to female and the male to male, and female to female too. So different kinds of jumper wires. Now, if actually, please let me know in the discussion board whether you have them. If you don't have them, I really don't have a good solution right here, right now, because they're supposed to provide. Unfortunately, we placed the order for a number of other things that also they have not arrived. Now, if the school has not provided you the male to female jumper cables, if you don't have them lying around, if you've been doing IoT projects, maybe you already have them, but if you don't have them, please just go, buy some of those from Amazon. With if you have a Prime, it'll be fast shipping. Just they're very cheap, just a few dollars. You can get a bunch. If you don't know which ones to buy, and let me know. I can find a couple of things for you. There's a lot of choices, by the way. And then you can easily find them. Just search for for example, IoT jumper wires, and then you should a bunch of things come out. Make sure that that pack contains male to female, and also female to female too. You already got the male to male, at least I think, and they provided those. I'm not sure if what I have is exactly what you have. You probably noticed that some of the things that I have, they're different from yours because they did not provide me some of those things. So anyway, this is kind of the challenge with this remote learning. If we're in a lab physically, it would not be an issue. So okay, either way, let me know if you have any trouble with this. Now, this is a this display you can display characters, and this is not really sufficient resolution for you to display much of image. And you can make in fact you can probably make emoticons, right? So that's something you can do as well, but I'll give you some examples later. Now, the first program we're going to use this, it's simply just going to print out hello world. And then right now, actually, under the reflection, you might see a hello world already written here. Kind of faint color. It's hard to see because it's not the the backlight is not turned on. Okay. Now I want to kind of point out, right, this particular case, the power line, the VCC, right? When you connect that to a 5 volt pin. The 5 volt, you have 2 of them at the top right corner of the extension board and or the GPIO pin layout. And typically, whenever you connect the devices, be very careful not to connect 5 volts. You may potentially damage your Pi and your device as well. So only when you're certain you know what you're doing, then you connect the 5 volts. A lot of times, in order to connect to 5 volts, you have to put some other components in between to protect the devices. In this case, with the LCD, it turns out that it is good enough on its own. Okay. So that's it. There's basically just 4 cables to connect. You got a ground, you got a 5 volt, and then you have 2 data cables that goes to the SD1 and SCL1 pins. Those are at the top left corner. Okay. And when you're connecting cables, just always be extra careful not to connect to the wrong places. Those holes are pretty small on the breadboard, but just kind of pay attention to details. And again, when you connect the circuit, always turn off the Pi, power off it, right? And then once you got this connected, and you can turn it back on, okay? Now, so we have this thing connected here, and now let's simply write a hello world program, and I already have that ready to show you. Well, actually, before we do that, there's a couple things you need to be aware. So we are actually, so first of all, this device is connected, right? So when it comes to the I2C, every device has an address. This address is represented by a 7-bit number. So if you're presenting in, when we write the address in the program, we use hexadecimal notation. But the standard, the I2C uses 7 bits represent. So basically you can have up to 128 devices, and that's kind of the advantage of I2C. You can connect a lot of them to your system, okay, if you want to. And so every device has an address, and this address is an identifier of the device. And so we need to get this address of this LCD first. How do you do that? So there is a program. There's a program you need to run, in fact. And this program is called I2C detect. So you can just run this in the terminal once you get remote connected SSH to the Pi. And see here, actually, this is SSH this is the SSH session where we have a remote terminal opened up. This I2C detect program is already installed for you. You don't need to install this. And then we use sudo for elevated privilege to run this. You need that kind of permission. And then with -y and a 1. Okay, so there's the 1 is actually the port number. So when you run this, it will show you a table. And as I mentioned, this table actually provides just a simple mechanism for you to read the address of your device. And so here, actually, we see a single number in this table. And so this table, this address here is shown as 27. And by the way, this is a hexadecimal notation, all right? And the 27, it becomes the address for your device. okay? Now, this little program here is a simple test. And this is using the SM bus library. SM bus we just mentioned in the lecture. In the slides is the system management bus protocol, which is a subset of I2C. So you can use this to interact with your I2C device. And so this is simply, we actually first make an object of SM bus, given the bus number, which is 1, right? And then you can use this bus object to write data. So here we say we're gonna write a byte of data and sending that data to this address, and this address representing that device. And basically the data sent to this address, and then basically then gets received by the LCD. And the data we're sending is actually, yeah, the data we're sending is that we're also going to use the address 0 register, and it has a register reserved for the device, and then we're going to say it's 0, and then the value is 0, 1. So 0, 1 is the value. So I'm just going to look at this documentation of this method here for bus object. And what this ends up doing is actually turning off the backlight. So we're sending this data, and this has a specific meaning in this case. Now my screen is already turned off, so I can't really show you this in action, but I'll run this again after we have displayed Hello World. In the Hello World program, we're going to use a library called RPLCD to get this library. This library is not installed as part of Pi, and so you need to install it for your Python. So the way to install it, you run this sudo python3-m pip. We're using the pip tool to install RPLCD. Now mine is already installed, so you will see, it will say it's installed, but in your case, well, actually, successfully installed. Oh, you know what? So anyway, it just kind of reinstalled when I ran this thing. Looks like this is it's fine. So this, you just use this to install it, and then this little program here, you'll get access to this. There's just a couple lines. First, we'll create an LCD object, which is an object of class char LCD. Char stands for character. There's a couple of things we'll provide. First is we need to specify the I2C port expander. What's a port expander? Port expander really is the fact that LCD exposes the backpack. If you look at the backpack, the I2C backpack, it has 4 ports coming out. And in fact, the LCD has 16 ports. There's a port expansion going on here for this to be connected. So there's a chip that controls the port expansion here. And this chip is let me actually switch to the camera. Now, I assume if you got this kind, and then your chip is probably similar to mine. In this, on the backpack, you see this little black square in the middle. This is an integrated circuit. This little chip here has a printed name on top, and try to read off this name, and this is the name you need to put into this initialization call for the object. So let me go back to the code. So mine is PCF 8574. It may ends with a letter T, but letter T is not necessary. But there's a specific there's actually only two kinds of expander will be accepted. And I think yours is probably the same as well, but read, we'll see what it is. If it's different, let me know, and then they should accept a different value. There's two values it will accept. Let me see if we can find in the documentation. The documentation says, all right, so they say that there's three kinds were accepted. There's MCP 2300A, MCP 23017, in addition to the PCF that I'm using here. This is what I have. And I suppose yours might be the same, but just make sure that's the same thing. So provide this value to the I2C underscore expander. And the address is this address we just read, 27 in hex. So starts with 0x, that's how you write it, literal hex number. The port is 1. That's the bus number or the port number. It's always 1. And there's a 0, but 0, it has a special purpose. And don't worry about that 0. You're not going to use 0. And then you also specify the columns and rows of the LCD. There's 16 columns, there's 2 rows of characters you can specify. So this is the one that I have. I think yours should be the same. And just make an LCD object like that. And then, simply just use the right string function or the method on the LCD object to print out hello world on the LCD. And just let me kind of step back, talk about this library. This library made it super easy to deal with LCD. And underlying this, it uses I2C protocol. Actually, in this case, it's using the SM bus subset of the I2C to communicate. And there's a lot of lower level function calls to make to, handle the actual protocol dealing with, remember that data transfer chart I showed you with the timing of things and the pulses. And that's what the underlying things have to deal with. So it's pretty lower level, but this is a fairly high level library, which is very easy to use. Because that's why I kind of, just suggest you to use this. But I want to, mention that it is underlying that is actually using the SM bus in this case. Now, this library supports different different libraries. It's built on top of other libraries. SM bus, it has its own library. And if you connect the LCD directly to the Pi without the I2C backpack, means it will communicate directly without the backpack, without using the I2C protocol. That's possible too. But again, with I2C, things will be, easier to do. And it's a sort of more of a standard way of communicating. All right. And so I got this little program here that's actually just run this. Let me switch to the camera. And let me hold on to this. Let me hold this a little higher so you can see a little better, hopefully, okay? All right, I'm gonna run this. That's it. It's hard for you to see in the camera because the backlighting makes it impossible for the camera to show you the hello world on top. But again, if I turn off the backlighting, now this is the good time now for me to show you around the other. Remember the test I said this was to simply just turn off the backlight. Let me run that thing. And you'll see the backlight is turned off. And you actually see hello world right now in camera, right? Yeah. So is the camera effect. And so hopefully when you're running it, you'll see when the backlight is on, you'll see the hello world very clearly on the screen. Okay. Now that's actually what I have to show you today. I'll show you a couple more examples how to use the LCD in the next lecture.